Previously, we looked at the undamped 1 degree of freedom system and found the solution for vibrations. Now we will increase the complexity a little bit and we'll look at the damped system in which we will be modeling the energy dissipation. Energy dissipation will be modeled by, as you see here, by the damper element in which the uh, damping force is proportional to the velocity. So the equation of motion now contains a damping term, Cx dot term in itself. So what we do is we will try to find the solution to this equation when there is an initial condition given to this system. We will try to analyze it first. What we do is we take the physical equation, now we non-dimensionalize it by dividing it by m, in which case we get k over m becomes the natural frequency squared, and c over m becomes the 2 zeta omega n term, from which we can find the zeta value, which is a non-dimensional term describing the damping ratio. It is the viscous damping ratio. We will see its consequences. So we have the equation of motion in the non-dimensional form written as such: x double dot plus 2 zeta omega x dot plus omega n squared x is equal to 0. Now this is a second order linear differential equation which can be modeled, which can be solved. And the solutions to this is in the form of exponentials. And these exponentials might contain complex roots. And if the roots are complex, we will see that the response will be oscillatory. And A and B are the terms that depend on the initial conditions, that is, initial velocity and initial displacement. So once you insert this exponential into the equation of motion, you will get solutions for the roots, what we call alpha here. And we find that the alphas from this insertion is equal to the following: zeta omega n plus omega n times in square root zeta squared minus 1. Depending on the value of zeta, the solutions change their character. For example, if zeta is 0, completely 0, we have roots are purely imaginary. They would be equal to square root of minus 1 times omega n, which would be I times omega n. That would be an undamped system, but we studied this case. We looked at the undamped case, so we are not going to look at it. Undamped case is basically sustained oscillations, simple harmonic motion, sines and cosines without any damping. More interestingly, if the damping ratio is between 0 and 1, if zeta squared is less than 1, this term inside the square root is negative. So you have complex roots, and we have underdamped system. If zeta is 1, the square root term just cancels. So roots are zeta times omega n, and they are repeated. Such a system is called critically damped. And if zeta is greater than 1, the roots are real, and the system is overdamped. Most important case for us is the underdamped case, in which case there would be oscillatory motion. The motion oscillates and eventually dies out because of the dissipation of energy. So you start from an initial displacement and a possible initial velocity. Initial velocity gives you the slope of the curve when time is equal to 0. The roots are complex. The general solution is, well, using Euler's identity, you can find that eventually the equation that solves your system is something like this. An amplitude times sine omega t plus an envelope that decays over the time. So exponential term decays over the time, and inside it, the red thing oscillates, as you see, and it goes to zero eventually. The response goes to zero because this is a free system. There are no external energy input to the system. One thing that is important is that the frequency of oscillation. This is still the frequency of free oscillations, but we are using here not the natural frequency omega n anymore, but rather the damped natural frequency, which is omega d. Omega d is simply 2 pi over the period of damped oscillations, Td. Therefore, the damped period is 2 pi over omega d. And omega n and omega d are kind of related. Omega d, damped natural frequency, is omega n times 1 minus zeta squared. If zeta is small, you can take omega d to be omega n, but in general, they differ with it from each other. Frequency of oscillations in the damped case is different. Remember that. If you have an overdamped case, these are not very common in vibrations, but in that case, the roots are real and the oscillations are well, there are no oscillations actually. The response is non-oscillatory. Its response is simply a combination of two exponential decays. Critically damped case is more interesting. The roots are real. The solution becomes something like this. The roots are repeated, I'm sorry, and real. Now, if you look at it, the cases, for example, the underdamped case oscillates like this. Another underdamped case in which the damping is higher, you have oscillations that die out quickly. Critically damped case dies out fastest compared to other damping cases, meaning, well, yeah, it is the fastest dying out damping case. And the overdamped case usually takes out a longer time to die out. So the critically damped case has a maximum rate of decay. And that is used in many applications. For example, in large guns, you arrange the dashpot so that there will be critical damping, or the door closing mechanisms might have critical damping. Now, there is another thing. The logarithmic decrement is used in the analysis of damped systems. This is especially useful in order to determine the damping ratio experimentally. That is, if you have a system in which you want to find the damping ratio, you might do an experiment on that system and determine zeta from using this concept of logarithmic decrement. How does it work? It works as follows. If you have a damped oscillation, one peak, let's call it one peak of your oscillation is, let's call it at Tm. Here, this is Tm. The second peak, next peak, is Tm plus 1. So in between, you have the period, damped period, T. I will call T, or you might call it Td if you like. That much of time goes on between one peak and another peak. If you can measure the values at those peaks, you can measure x of Tm and x of Tm plus 1. These are measurable, supposedly. If you plot these curves, you can measure them, or, you know, acquire data, you can measure them. Now, the solutions to each of these are as follows. Well, I used x before, here I use c. It is an exponential envelope times the amplitude times a sine term. And for the second one, Tm plus 1, you have the same thing for time equals Tm plus 1. Now, Tm plus 1 is equal to Tm plus capital T. You can write, let me write it here. Tm plus 1 is equal to Tm plus capital T. What that is Tm plus capital T is 2 pi over omega d. And omega d, as you remember, was omega n times root 1 minus zeta squared. Okay. Now, if you put it inside the sign, this Tm plus 1, you have Tm plus 2 pi. But if you add a 2 pi to a sign, you get the same value itself. The value of sign does not change. So these terms, these sign terms, you have, if you divide Tm by Tm plus 1, what you get will be these C terms are going to cancel. These sign terms are going to cancel. And you are going to be left with these e to the something terms. And you can subtract them from each other since they are division. It is Tm minus Tm plus 1, but there is a minus here. So it becomes Tm plus 1. This becomes a plus and this becomes a T. But T is 2 pi over omega d, as we have said. And 2 pi over omega d is omega n times 1 minus zeta squared. So Tm over Tm plus 1, x of Tm over x of Tm plus 1 is equal to e to this term. Now, the trick is to take the logarithm or the natural logarithm. So this is the term we had in the previous slide. We take the natural logarithm of both sides, of this side and of that side. E to the something term, just e to the something cancels ln. And the ln of x of Tm over x of Tm plus 1 is called the logarithmic decrement. Logarithmic decrement is defined as natural logarithm of one peak divided by the next peak of the response. This peak divided by this peak, and you take the ln. And we found out that it is equal to 2 pi zeta over 1 over zeta squared. Now, let me carry myself here. This is equal to 1 over zeta. If zeta is a small number, zeta square is even smaller. So you can approximate delta, in this case, by 2 pi over 2 pi zeta. And if you look at it, for values of zeta less than, let's say, 0.3, it is okay. Okay, this is how we plot. This is the real expression, and this is the linear expression, 2 pi zeta expression. So if zeta is less than 0.3, it should be okay, this term. And once the delta is known, we can find logarithmic decrement simply by finding two peaks and taking ln. We can solve for zeta from this equation. The exact solution is this one, delta over 2 pi squared plus delta squared. But if zeta is small, you can use delta is equal to 2 pi zeta, from which zeta is equal to delta over 2 pi. This is the quick solution. Sorry. This is the quick solution for zeta equals, zeta is small, like less than 0.3. So having found delta, we can find zeta, the damping ratio, which is a good thing. But the problem is you might not be able to find two peaks next to each other, but rather you might be able to find measure lots of peaks and find a more accurate response. Let me plot something here. Let's say that the response looks like this. Say that this is x1. This is, let's say, is xn. So you have n peaks from here, this one, etc. You might have more. We want to find the ratio of the first peak to the n plus 1 peak. This is n plus 1 actually. We say this is xn plus 1. So that there are n peaks in between x1 and xn plus 1. So we divide them to each other, x1 over x2, x2 over x3, xn over xn plus 1. And this is equal to x1 over xn plus 1. Now, each of these is equal to, we know that, where is this? It's here. Each of these is equal to e to the zeta omega nt. This one is also equal to zeta a to the omega nt. And we have n of these. N of them multiplied gives you e to the n zeta omega nt. If you take logarithm of this equation now, ln of x1 over xn plus 1 is therefore n times zeta omega nt. So, which is equal to, as you remember, n times delta, right? If you look at the definition of delta, this was delta if we had found out in the previous slide. So it is n times delta. So delta can be found out simply by taking the ln of x of t and then dividing it by x of t plus n capital T and dividing it by 1 over n if there are n oscillations in between. Okay. So this is another way of finding the logarithmic decrement if they are separated by two different cycles. And this is the logarithmic decrement in terms of physical parameters if it's necessary to find it. So this concludes the theoretical part of the damped oscillations.